You have a normal or a Gaussian distribution. So a random variable is distributed according to a normal under a given mean and variance, and you know how this looks like. The first term is the normalization constant, but where does the second term come from? We can actually derive it from a maximum entropy principle, which we will do in this video. Hi, welcome to this new video. In an earlier video, we already looked at how we can intuitively come up with this expression, that we have the exponential of minus another constant and then the x minus mu in brackets squared. But we can also find a more mathematical way why this must be the correct form of describing a normal or a Gaussian distribution. This video will be a little more technical. It's not 100% relevant to understand normal or Gaussian distributions, but I think it's something really, really beautiful. What we are using is the fact that the Gaussian, and I will use the name Gaussian and normal interchangeably in this derivation. So our normal is maximizing the entropy under prescribed mean and variance. And of course, recall, we can either define the normal with the standard deviation, which is just the sigma, or with the variance, which is the standard deviation squared. And I talk about entropy. Since we have a continuous random variable, we have to look at so-called differential entropy, which is just a complicated word for saying that we are working in terms of integrals instead of in terms of sums. And the entropy is given as h of p, as the integral from minus infinity to plus infinity, actually it's a negative integral, of p times ln p dx. P is the probability density function that we are looking for, or that we are plugging into the entropy, so it's dependent on a p of x. And here also we have a p of x, and here p of x. So we are integrating out the dependency on x. And this might ring a bell. That is a functional. Here the entropy is a functional. And a functional was nothing else than a function of functions, because it is taking in a function or a distribution, and it is putting out a scalar value that is the entropy of this distribution. And entropy is encoding the randomness inside this distribution. So actually what we will be doing is we will be showing that, or we will use the fact to derive that the Gaussian or normal is maximizing this functional under prescribed mean and variance. So let's put this mathematically. So we say that the p of x star, or the function, and we will see it will be the normal and Gaussian, is the arc maximum over all possible distributions or functions applying to the functional of the entropy, subject to three constraints. First, it has to integrate to 1. Okay, this makes sense. This is because of the normalization. The next constraint is that the integral over p of x times x dx is mu. That also makes sense because that is the prescribed mean. The mean is nothing else than the first order moment of a distribution. And the last constraint is that p of x times x minus mu in brackets squared dx should be sigma squared. And that is nothing else than the second centralized moment. So let's also put this down. This is the normalization. This is the prescribed mean with the first order moment, which is nothing else than the first order moment of distribution. And here we have the prescribed variance, which is the second order central moment. And we will be doing something that is kind of like simplifying our lives. We know that maximization and minimization is interchangeably, and we will use the following expression that we will minimize the negative entropy. This is equivalent to the arc minimum over all p of x, of course subject to the same constraints of the negative entropy. And recall, we have the entropy defined as the negative integral, and the minus minus is plus. It's just a handy thing. And of course, recall, we have a constraint optimization. So we have the three constraints here. So we have to build a Lagrangian in order to incorporate the constraints into our target function, and then we can do an unconstrained optimization. Let us note this down. We build a Lagrangian. And the Lagrangian is given as, some sort of like a mixture between a function and a functional. It takes first the p of x, or the p, which is the distribution, but then it also takes three more scalar values, which are lambda 0, lambda 1, and lambda 2. And it is defined as follows. We have the integral over minus infinity to plus infinity over p ln p dx plus lambda 0 times the first constraint rearranged for 0, and we will just bring the 1 on the other side by minus 1, and then we are getting opening brackets integral from minus infinity to plus infinity over p of x dx minus 1, then plus the next constraint rearranged for 0, which will be the lambda 1 times the integration from minus infinity to plus infinity over p of x times x dx minus mu. And then lastly, we have lambda 2 times opening brackets the integration from minus infinity to plus infinity over, well, this is nothing else than the second centralized moment, so it's p of x times x minus mu in brackets squared dx, and then minus sigma squared. Then let's bring the Lagrangian in a simpler form, where we have one big integration plus some scalar values. So this is equal to the integration from minus infinity to plus infinity over p ln p, which was our target, plus lambda 0 times p, which is from the first constraint, then plus lambda 1 times p times x, which is from the second constraint, and then from the last constraint we have lambda 2 p times x minus mu in brackets squared dx. And then we have to add the scalar values, and they will be just lambda 0 or minus lambda 0 minus lambda 1 mu minus lambda 2 sigma squared. And so our Lagrangian is consisting of the integral here, which is a functional minus some scalar values. So let's note this down. This is another functional. So another functional, and maybe you can think of it as like some sort of an augmented functional, and these are just some scalars. Since we now have an unconstrained optimization problem, we can just take the derivative and set it to 0. So this is what we will be doing over the next lines. So take derivative and set to 0, and we have to take the derivative with respect to p, our function, and then with respect to all our three scalar Lagrange multipliers. For this, let us start with the functional derivative of the Lagrangian with respect to p. And recall, this is a little confusing because in terms of functional derivatives, we always think of Lagrangians being whatever is inside the integral, but now our Lagrangian is in terms of the Lagrange multipliers. So be cautious, there are multiple definitions for the same name. And we have to set this to 0, right? And we of course would do the functional derivative by the Gaussian derivative, but in an earlier video we've seen that in this case, if we just want to minimize a functional, we can also just take the derivative of whatever is inside the integral with respect to p, but just a partial derivative, which is because we don't have any p primes in here. And this will then be equal to the derivative of, and let's call this what is inside this, we call this like a small l, just to give it a name, and define this as small l. So this is equal to small l with respect to p, but just a partial derivative. And we can do this, of course, because outside of the integral, we don't have any p's anymore. So they would also just vanish to 0 in the functional derivative sense. Okay, let's perform this functional derivative or this partial derivative because we use a simplified form. And when we get first, here we have to use the product rule. So first derive p, and then we're getting ln p. Then we derive ln p, and we get p over p. Then here we have plus lambda 0 plus lambda 1 x. And then here we will be getting plus lambda 2 in brackets x minus mu squared. And that's our first derivative. Then let's continue with the next derivatives of the Lagrangian with respect to lambda 0. And now we just take the classical partial derivative because, again, lambda 0 is a scalar as the other lambdas are as well. If we go back up, then we see, well, we are left with the integral over p dx and then minus 1. So this will be the integral from minus infinity to plus infinity over p dx minus 1, which has to hold to 0. And then we do the next, the partial derivative with respect to lambda 1, and we're getting the integral from minus infinity to plus infinity over p times x dx minus mu, which has to hold to 0. And we have the partial derivative with respect to lambda 2 over the integral from minus infinity to plus infinity over p times x minus mu in brackets squared dx minus sigma squared, which has to hold to 0. And of course, c, as it is always with Lagrangian multipliers, when we derive with respect to the multipliers, we're getting back our constraints. Now let's give these equations some names, and I will call this the first equation, this will be the second, this will be the third, and this will be the fourth. Again, recall we want to set it to 0, and now we want to solve for p, but this seems really cluttered, so we have to go step by step by step, and let us start with 1 and rearrange this for p. So let's start with 1, and what we will be doing is rearrange for p for our distribution. And we are getting, let's bring the ln p on the other side of the equation and multiply everything by -1. Then we are getting ln p is equal to -1 minus lambda 0 minus lambda 1x minus lambda 2 x minus mu in brackets squared. Okay, let's double check. So the -1 is from the p over p, then the lambda 0 is from the lambda 0, then the lambda 1x is from the next, and the last is from the second order centralized moment. Let us resolve this square here, and then we're getting -1 minus lambda 0 minus lambda 1x minus lambda 2, opening brackets, x squared minus 2x mu minus or plus mu squared, brackets closing, and then we can multiply lambda 2 with whatever is inside the bracket, and then we're getting -1 minus lambda 0 minus lambda 1x minus lambda 2x squared plus lambda 2 2x mu plus mu squared, or maybe let me rearrange this to be lambda 2 mu x. And of course, this should be a minus here. And now we can see that we have a quadratic equation in x here. Recall that the p that we want to find is a function of x. So it's the distribution over x. And we find these x's here, here, and here. Let us bring this in the standard format for quadratic equations. And then we have minus lambda 2x squared. And then let's collect everything that is in front of the x. And then we will be getting plus opening brackets 2 lambda 2 mu minus lambda 1 in brackets times x. And then we are left with everything that does not depend on x, which is -1 minus lambda 0 minus mu squared. Okay, let's denote down the coefficients that we have for our quadratic equation. This is an a, this is a b, and that is a c. So we have a is minus lambda 2, b is 2 lambda 2 mu minus lambda 1, and this is a c, which is -1 minus lambda 0 minus mu squared. And then we can also formulate this equivalently as ax squared plus bx plus c, right? And we did this because we want to rearrange this equation in order to have one term with x squared only. And the technique that we will be using is called completing the square. And if you are unfamiliar with this technique, then I would recommend you to check out my video on where I explain it. And the technique of completing the square is given as expressing this as an a times x minus d in brackets squared plus an e. We define this as follows, that a is a, and d is given as minus b over 2a, and e is c minus b squared over 4a. Well, then we can plug in what we had for abc into these equations, and we have a is, again, minus lambda 2, and d will then be, let's just plug in really stupidly what we have. We have minus, and in the numerator we have 2 lambda 2 mu minus lambda 1 over 2 times minus lambda 2. Let's simplify this. The minus and the minus is a plus, and we are getting 2 lambda 2 mu minus lambda 1 over 2 lambda 2. And then let's create two independent fractions out of this, and we have mu minus lambda 1 over 2 lambda 2. Then let's also solve for the e, and for the e we are getting, well, let's plug in what we have for c, which is -1 minus lambda 0 minus mu squared. And then for the b we have, so we have a minus, and b is in brackets 2 lambda 2 mu minus lambda 1 squared over 4 times minus lambda 2. And we can also simplify this a little bit and put in again -1 minus lambda 0 minus mu squared, and then we can multiply with lambda 2 over lambda 2, and we're getting, well, the minus minus is a plus, so we have the lambda 2 times the 2 lambda 2 mu minus lambda 1 over lambda 2 in brackets squared. And I see, well, this is a little like cut off. I'm really sorry for this, so I'll move it a little bit more to the left. And then we get -1 minus lambda 0 minus mu squared plus lambda 2 times, and then in brackets we're getting the same as we have here, which is nothing else than mu minus lambda 1 over 2 lambda 2, because I forgot the 2 here, because 2 squared is 4, then it makes sense. And surely a closing bracket. Well, then let's put it together in our expression, and recall we said that ln p of x surely is nothing else than a times x minus d in brackets squared plus e. So we will get a was minus lambda 2, and x is x minus, and d we calculated to be mu minus lambda 1 over 2 lambda 2, brackets squared, and then we add the e, which is -1 minus lambda 0 minus mu squared plus lambda 2 in brackets mu minus lambda 1 over 2 lambda 2. And let's apply the minus here in order to simplify the expression. Then we have minus lambda 2 times x minus mu plus lambda 1 over 2 lambda 2 in brackets squared -1 minus lambda 0 minus mu squared. Well, this is everything we just keep. And then we have in brackets here the last term. And of course I forgot the square here, which is quite crucial. So let's put this down everywhere we have it here. Now let us make a definition for which we want to shift our x into another variable, and we will define a y to be whatever we have inside this square term, and this x minus mu plus lambda 1 over 2 lambda 2. And with this, we can just write minus lambda 2 times y squared. And I hope this also gives you a little meaning why we did the completion of the square, because we then only have y squared left and we don't have any linear components in y. So this would then lead to the following, that we have minus lambda 2 y squared minus 1 minus lambda 0 minus mu squared plus the lambda 2 times the mu minus lambda 1 over 2 lambda 2 in brackets squared. And then again, recall we had nothing else than the ln of p, so let's apply the exponential on both sides of the equation, and then we get p of y is the exponential, or e to the power of minus lambda 2 y squared minus 1 minus lambda 0 minus mu squared plus lambda 2 times mu minus lambda 1 over 2 lambda 2 in brackets squared, and then closing bracket for the exponential. And with this we rearranged our equation for x or for y, and then we can now plug it into another constraint, and we will plug it into the third equation, or in other words the second constraint. And recall this was given as the integration from minus infinity to plus infinity over p of x times x. The x is mu. But now we have a distribution over y instead of x, so we also have to shift the integral. And for this, we will rearrange y for x, and we can do this as follows and get x is nothing else than y plus mu minus lambda 1 over 2 lambda 2. And then we can just plug it in. And since it's just a shift, this does not change the differential, so we don't have any distortion here. And also the limits do not change because minus infinity to plus infinity this kind of keeps. And this will turn our constraint into the equation from minus infinity to plus infinity over p of y times, and then for x we had y plus mu minus lambda 1 over 2 lambda 2 dy, and this equals mu. And then we can of course plug in our p of y here, but this won't help us much because then we are kind of stuck with an integral, and for this we will first make some splitting of the integral into two parts, and we are getting the integral from minus infinity to plus infinity over p of y times y dy, plus the integral from minus infinity to plus infinity over p of y times mu minus lambda 1 over 2 lambda 2 dy, and this has to be equal to mu. And what we see here are two integrals that we can actually solve, and the first one will be 0. And I don't think it's quite obvious why, so let me give you a little primer on why it is 0. And this is because, so equals 0, and this is due to the symmetry of the Gaussian. Right now we don't know it is the Gaussian yet, but we might have the suspicion already because we have exponential of minus y squared. And these others are just like some constants. We will figure them out, but this minus y squared, this reminds you of the bell shape. If we look at the distribution of what we just have, well, it's not a full Gaussian yet, but let's just assume it is one. And then we get a shape that is something like this, right? The integral that we want to solve here is the shape of the Gaussian multiplied by y. And y is nothing else, so this is our p of y, and y is nothing else than a straight line going through the origin with the slope of 1. This is y, right? If you just map y to y, this is like 1 times y, right? If we then multiply the normal with this one, we will see that we will be getting something like, this is a little hard to draw, but I think you see where I'm getting with this. So it is kind of symmetric. So this area here on from minus infinity all the way to 0 is the same as this area here from 0 to plus infinity. And that's the reason why it cancels. And you also call it just the symmetry of the Gaussian, and then it vanishes. So that's it vanishes. Then with this in mind, let us simplify the expression above, and then we're getting 0 plus the integral from minus infinity to plus infinity over p of y times this expression, which is mu minus lambda 1 over 2 lambda 2 dy, and this has to be equal to mu. And we see this here is just a constant factor. It does not depend on y, so we can put it outside of the integral, because constant with respect to y. And then we are left with mu minus lambda 1 over 2 lambda 2 times opening integration from minus infinity to plus infinity over p of y dy is equal to mu. We notice this is nothing else than the normalization of our distribution, because we know that if we integrate from minus infinity to plus infinity over any distribution, then equation 2 holds, which was the normalization constraint. So this is 1. So this is 1 because of the second equation or the first constraint. And then we have mu minus lambda 1 over 2 lambda 2 is mu. Then, well, mu cancels. We have minus lambda 1 over 2 lambda 2 is equal to 0. Then we can multiply by 2 lambda 2, but you already see where I'm heading. Lambda 1 is 0. And that is the first solution that we have to our optimization problem. Congratulations, it has been a long journey so far, but there's more to come. So we found lambda 1 to be 0. Well, then we can plug this into our p of y. So plug lambda 1 is 0 into p of y, and then we have p of y was nothing else than the exponential of minus lambda 2 y squared minus 1 minus lambda 0 minus lambda 2 mu squared plus lambda 2 times in brackets lambda 1 over 2 lambda 2 minus mu in brackets squared closing brackets for the exponential. And if you've watched carefully, then you just see that I missed this lambda 2 in all the derivations beginning at the top, which is quite unfortunate because I literally forgot to multiply with lambda 2 here. So let me just put it here and so on and so forth. But the notes that are in the video description, they will be sanitized with this mistake. But never mind, let us continue. Then let's plug in the lambda 1 is 0 in here. And then we see that this will be 0. And then we have p of y is the exponential of minus lambda 2 y squared minus 1 minus lambda 0 minus lambda 2 mu squared plus lambda 2 mu squared, and then it also works that these two cancel. Then we can also go back to x, and we say that y was nothing else than x minus mu plus lambda 1 over 2 lambda 2, and then this will also be 0 again. And then we have our p of x, and we are getting closer to the Gaussian step by step, and we have a minus 2 times x minus mu in brackets squared minus 1 minus lambda 0. Then we can make another substitution, and we substitute a set to be x minus mu, in order to again have just an squared on a quantity here, and we have p of z is the exponent over minus lambda 2 times z squared minus 1 minus lambda 0. And we've used the third equation, which is the second constraint, but now we want to go on and use the second equation, which is the first constraint. So plug into the second equation, and recall the second equation was the integration from minus infinity to plus infinity over p of x. The x is 1. And since we made a substitution, we have to check if anything changes within our integral, but x will just become z. So if we rearrange this, then x is just z plus mu. There is no distortion since we just have a shifting, and also the limits of the integration do not change. So we just have that this is equal to the integral from minus infinity over p of z dz has to hold to 1. Then let's plug in what we have here, and then we have the integral from minus infinity to infinity over the exponential of minus lambda 2 z squared minus 1 minus lambda 0 dz has to be equal to 1. Let us simplify the expression inside the integral by putting these two components in the exponential outside of the integral because they are constant. So we will be having the exponential of minus 1 minus lambda 0, this is nothing else than e to the power of minus 1 minus lambda 0, times the integral from minus infinity to plus infinity over the exponential of minus lambda 2 z squared dz, which has to hold to 1. And you might have seen this before. This is similar to what we did in the video on deriving the normalization constant for the Gaussian. So let me note this down. So this is similar to normalization derivation, and in the normalization derivation, we made a trick that we squared this integral, then made some changes, polar coordinates, and so on and so forth. But anyways, if you generalize what we did there, then you will get that this integral is the square root of pi over lambda 2. And then we are left with the expression that e to the power of minus 1 minus lambda 0 times the square root of pi over lambda 2 is equal to 1. And I will call this expression star because we can't solve it yet, because we first have to find another equation for these two parameters or for these two variables in order to be able to solve it. And for this, we will plug p of z into the last equation that we have left, and this will be equation 4, and this is the constraint on the second order moment, and the equation was given as the integral from minus infinity to plus infinity over p of x times x minus mu in brackets dx is equal to sigma squared. Well, then again, let's plug in our shift in x, or the substitution that we made for x, that we made it a set, and the x is z plus mu. So we can plug this in, and then we get the integration from minus infinity to plus infinity. Again, the limits of integration don't change since we have an integration, since we just have a substitution that is a shift, and we have the p of z times, and x was z plus mu, and then minus mu from what we had before, bracket squared dz has to be sigma squared. And then you see the mu and the mu cancels. We are left with the integral from minus infinity to plus infinity over p of z times z squared dz is sigma squared. And if we then plug in what we had for the p of z, then we get the integral from minus infinity to plus infinity over the exponential of minus lambda to z squared minus 1 minus lambda 0, closing brackets for the exponential, times z squared dz is equal to sigma squared. And then we can again make the same trick to put these constants in front of the integral, and we have the e to the minus 1 minus lambda 0 times the integral from minus infinity to plus infinity over the exponential of minus lambda 2 z squared times z squared dz is equal to sigma squared. And this integral is now a little more tricky. There are some standard forms, but we can also derive why this integral has to be the case. And recall, in the last equation that we arrived by, the constraint that we used the equation that the integral from minus infinity to plus infinity over the exponential of minus lambda 2 z squared dz is equal to the square root of pi over lambda 2. And let's call this an f, which depends on lambda 2. So the value of this integral is dependent on lambda 2. I think this makes sense because lambda 2 is on the right hand side of the equation. We know that the integral that we're getting here is the same as if we would derive the f with respect to lambda 2 and put a negative sign in front of it. Because if we do this, then if we take the negative derivative of f with respect to lambda 2, then this is the integral from minus infinity to plus infinity, because the differential operator propagates over the integral. And then we take the derivative of this, and we will be getting the outer derivative is just the exponential of minus lambda 2 z squared dz. And the inner derivative will be, well, this derived with respect to lambda 2 is minus z squared, but we are applying another minus here, and then this cancels, right? And we know that this will be the square root of pi over lambda 2, and then this will be the derivative of this with respect to lambda 2. So in other words, what we are getting here is that e to the minus 1 minus lambda 0 times something has to be sigma squared, and this something is the negative derivative with respect to lambda 2 of the square root of pi over lambda 2. And let's take this derivative, and this will be the derivative with respect to lambda 2 of pi to the 1/2, which is just the square root, times lambda 2 to the minus 1/2. If we take this derivative, then we are getting, well, pi to the 1/2 stays because it's just a constant. Then we get minus 1/2 times, and the derivative of this is lambda 2 to the minus 3/2. Plugging it all back together, we are getting the square root of pi over lambda 2 to the power of 3 and a 1/2 in front of it. And the 1/2 is, of course, negative. And we are getting e to the minus 1 minus lambda 0 times minus 1, because this is the minus from here, times minus 1/2 square root of pi over lambda 2 to the power of 3 is sigma squared. And then if we cancel the minus and the minus, we're getting e to the minus 1 minus lambda 0 times the square root of pi over lambda 2 to the power of 3 is sigma squared. And this will be our second equation. And of course, we multiply by 1/2 here. And then we have our two equations, and we are left with solving a system of nonlinear equations. So solving a system of nonlinear equations. The first equation was the one that we got from the first constraint or second equation, which was e to the minus 1 minus lambda 0 times the square root of pi over lambda 2 is equal to 1. And the second is one that we just derived here. I will note it down once again. It is e to the minus 1 minus lambda 0 times square root of pi over lambda 2 to the power of 3 is equal to sigma squared. And of course times 1/2. Let's rearrange the first equation for e to the minus 1 minus lambda, and then we are getting e to the minus 1 minus lambda 0 is equal to, well, we divide by this, so it changes the order in the fraction, and we're getting the square root of lambda 2 over pi. And the second equation rearranged for the same term will give us, well, 2 sigma squared, because we multiply with 2. So just like multiplication here. And then we divide by the term in the square root, and it inverts, so it's lambda 2 to the power of 3 over pi. Then let's set them equal here, and from this we are then getting that the square root of lambda 2 over pi is equal to 2 times sigma squared times the square root of lambda 2 to the power of 3 over pi. And we see we only have lambda 2 left, which is one of our unknowns. Sigma squared is prescribed, and the mu is just a natural constant. And in order to get rid of the square root, we take the power of 2 on both sides of the equation, and then we have lambda 2 over pi is 4 sigma to the power of 4 times lambda 2 to the power of 3 over pi. And then we see the pi cancels here, and we can also divide by lambda 2, and then we are left with lambda 2 squared. And then we have lambda 2 squared is, well, we divide by this. Here we will have a 1, so it will be 1 over 4 sigma squared. And then we're taking the square root, and we're getting plus minus 1 over 2 sigma squared. And now there are two possible paths. Either we go by the plus or the minus. And we will see if we take the minus, then we will lead into a dead end. You can check this for yourself, but we have the plus in order to enforce that sigma is greater than 0. So I will write this down. So we need the plus. And then we have that lambda 2 is plus, but I don't write it down, 1 over 2 sigma squared. And with this, we found our next parameter or our next unknown. Fantastic. It's a long journey, right? Then we can plug this into the first nonlinear equation. So we plug this into star, and then we have e to the minus 1 minus lambda 0 times the square root of pi divided by 1 over 2 sigma squared has to be equal to 1. So this goes into the numerator, and we can take the square root of sigma squared, which will just be sigma, and we will leave the 2 inside of the square root. And we have e to the minus 1 minus lambda 0 times sigma square root of 2 pi equals 1. And well, now you see, oh, this is kind of close. I've seen this before, but bear with me. These are the last meters of our sprint here. And let's rearrange. And we have e to the minus 1 minus lambda 0 is 1 over sigma times 2 pi. And then let's take the logarithm, naturalis on both sides. And then we have minus 1 minus lambda 0 is the logarithm. So we just take a minus in front of the logarithm in order to invert our fraction here. And we have minus ln of sigma times the square root of 2 pi. And then let's rearrange for lambda 0. And lambda 0 will then be the ln of sigma 2 pi minus 1. And then we have our last unknown. Wow, what a nice journey. Okay, let's plug this all into the p of x. And recall the p of x was given as p of x is the exponential of minus 2 in brackets x minus mu squared minus 1 minus lambda 0 closing brackets. And then let's plug in, and we have p of x is the exponential of, and lambda 2 was, recall, 1 over 2 sigma squared, so minus 1 over 2 sigma squared x minus mu in brackets squared, then minus 1 minus, and then let's plug in this, which is the ln of sigma square root 2 pi minus 1, and the minus will be a plus, and then we have minus 1 plus 1, so this cancels. Let's write this down again. So we have the exponential of minus 1 over 2 sigma squared x minus mu in brackets squared minus the ln of sigma times square root of 2 pi closing brackets for logarithm and for the exponential. And then we can split out, since we know if we have an addition or subtraction in the exponent, and this is the same as if we would multiply e to the power of this times e to the power of this. So we have the exponential of, and also change the order here, minus the logarithm of sigma square root of 2 pi times the exponential of minus 1 over 2 sigma squared in brackets x minus mu squared. And then the exponential cancels with the logarithm, and the minus of the logarithm will be 1 over this expression. So we have 1 over sigma times 2 pi times the exponential of minus 1 over 2 sigma squared x minus mu in brackets squared closing brackets, and that is our p of x. With this extremely long journey, we arrived at the Gaussian or normal distribution. And by this we've shown that the Gaussian or normal is maximizing the entropy under prescribed mean and variance. And with many points where one could potentially fail or make a simple mistake, and I also made a simple mistake in this video, and the notes that are on GitHub, I will remove the mistake in them, so you can also take a look at them. And surely if there's anything within this derivation that was unclear, then please write a comment. I would be happy to answer it. And as always, if you enjoyed the video and the derivation, then please leave a like and a subscription. I would really appreciate this. Here you will now find similar videos, and I hope to see you next time.